Hello students, in this video we'll discuss common integrating factors that appear when solving differential equations that are not exact, not separable, or not linear. So we'll focus on two common differentials. The first differential we'll consider is d of xy, which we can compute using the product rule. It's the first function times the differential of the second function plus the second function times the differential of the first function. So when I see an expression of the form x dy plus y dx, I can write it as the differential of x times y. If we look at the differential of y over x, we'll have to use the quotient rule. It's the bottom times the differential of the top minus the top times the differential of the bottom over the bottom squared. So if we see this factor in our differential equation, we can replace it with d of y over x, and I can do the same thing for d of x over y. Also, we should remark that even if I don't see the 1 over x squared in the denominator, this expression x dy minus y dx will suggest d of y over x. So let's see how these differentials in conjunction with the substitution can help us solve a differential equation. Let's consider the following example. Let's consider x cubed y cubed plus 1 dx plus x to the fourth y squared dy equals 0. Now at this point we'll examine the differential equation. We see the differential equation is not separable, so this differential equation is not separable. There's no easy way to get all the x's and the y's decoupled. It is not exact. Indeed, the x derivative of this is 4x cubed y, since 4x cubed y squared, which is the x derivative of this term, is not the y derivative of this term, is not equal to the y derivative of this term, which is 3x cubed y squared. So it's not exact, and it's not linear. So our three standard techniques for solving a differential equation don't apply to this particular example, which means that I need to algebraically rearrange my differential equation and try to exploit some differential factors that we see. So what we'll do is we'll return to the original problem, and I will expand it out. I will have x cubed y cubed dx plus dx plus x to the fourth y squared dy equals 0. I'll simply just expand out that factor. And now I'll look at these two terms and notice that they share a lot of common factors, so I'll group those two terms together in my differential equation. If we do this, we will have x cubed y cubed plus x to the fourth, and these are the dx terms, plus x to the fourth y squared dy, and leave that solitary dx by itself. Now I'd like to make use of this formula that the derivative of x times y is x dy plus y dx. So I want to see a y dx over here. So what I will do is I will divide the entire equation by x cubed. If we divide the entire equation by x cubed, we will have y cubed dx plus x y squared dy plus dx over x cubed equals 0. And now from these two terms over here, I will pull out a common factor of y squared. So I'll pull out a y squared from those two terms. So I'll have a y squared, and then I will have an y dx plus x dy plus dx over x cubed equals 0. Now the two terms in parentheses are exactly d of x times y by our rule over here. So I can now write our differential equation in the following form. It is y squared times d of x times y plus dx over x cubed equals 0. And the final thing I will do is I will re-multiply the equation by x squared. If I do this, I will have x squared y squared dxy plus dx over x equals 0. Now we can examine this term, and I can call u x times y, and with this substitution our differential equation becomes u squared du plus dx over x equals 0, which is now separable, so we can integrate it to get u cubed over 3 plus the log of x is equal to c. And now we finally substitute in what u is. U is x times y, so we will have x times y cubed over 3 plus the log of x equals c is the solution of our differential equation. So by writing the differential equation with a substitution using these common differentials, we are able to solve the differential equation. Thank you very much.